So today what we're going to be doing is we're going to be talking about color. We're going to talk about color within lights, primary colors, secondary colors, complementary colors. We'll also talk about how the differences between color, light, and pigments and how they are actually separate. We'll also talk about how sunsets work and why they turn that nice red color and why the sky is blue. We'll also talk about ending up with talking about color blindness. So today is about color. So first off, the spectrum. When you take light and you spread it out into all the colors, the visible light we can spread out even more. And we can spread them out into the rainbow. This is called the spectrum. So spectrum just means spreading out. And the rainbow is just the spreading out of visible light into its rainbow colors or its different distinctive colors. The rainbow colors, the Roy G. Biv. White light is all the colors mixed together of light. So under white light, all objects appear white. The objects that are colored there are going to be colored that same color. It will reflect all colors of light and absorb none if it's white. Because white light reflects all colors of light, it is not really a color, but of all colors. Now black is the opposite. Black is the absorption of all colors. So an object appears black when they absorb all light. So we can have this nice white light beam coming in, hits a prism, spreads out into the rainbow. Black holes are black because they absorb all light, because no light can escape a black hole. And that's why they appear black. So the sun itself, right here, this is the sun's radiation. So everybody's like, what color is the sun? Well, everybody colors it yellow. But in reality, the sun is white. The reason we write it yellow is because here is where our eyes are most sensitive to. This yellowish green right here at the kind of the peak here. This yellowish green is where our eyes are most sensitive to, and thus our eyes kind of perceive the sun as a kind of a yellowish a yellow-greenish color. We say it's yellow just because it was easier when we were little kids, but right here is where our eyes are kind of most sensitive to. But the sun is just white. If you go to space, you'll see the sun is white. Now, because all objects absorb some kind of natural frequency of light, all objects will absorb a specific frequency. Now, that frequency versus the reflection of that depends on what kind of material that light is being shown on. A white surface, all light will reflect off of it, all visible light will reflect off of it. If it's a red object, only the red reflects off and everything else gets absorbed, and we see objects as red. If it's a black surface, nothing gets absorbed onto it. So, what color does the flower reflect? Well, if the petals, all gets absorbed except for the yellow light. But the green is all absorbed except for the green light. So here's a question. What color does photosynthesis need? If you say green, you'd be wrong because it reflects off green. Photosynthesis needs actually the reds and the blues. They need the opposite ends. And it needs reds and blues to actually use photosynthesis. Green is actually not the color they want. So if you shine a green light on a plant, it will actually die of starvation due to the fact that it needs reds and blues. Now, light has different colors. Those colors are what we call the primary colors. The primary colors are red, green, and blue. RGB. You may have heard that term before. RGB, specifically in TVs, that's the primary colors of light. Now, don't get that mixed up because a lot of people think, well, the primary colors, they start singing a little song they learned when they were in elementary school where it's like the primary colors are red, yellow, and blue. That is not true. Okay, that's a misnomer. The primary colors of light is red, green, and blue. And if you mix red, green together, you're going to make yellow. Now that seems counterintuitive because you're like, wait, no, red and green make brown. No, that's pigments. You're thinking paints. This is light. So blue and green mixed together make cyan. Blue and red make magenta. Now, when you mix two colors together, they create what you call this is your secondary colors, your magenta, yellows, and cyan. If you mix all three together, you get white. Now, if you mix a complementary colors are when they're across this wheel. Blue and yellow are complementary. Cyan and red are complementary. Magenta and green are complementary. And complementary, if you just mix green and magenta together, you get this tertiary white. Now these colors, these secondary colors, these are again light, not to be confused with pigments or paints. You'll want to write this down because you're going to want to know this. All right, now subtractive colors is also known as pigments. These are the colors found in paints. And the primary colors are yellow, cyan, and magenta. When we were in elementary school, it was easier just to call this red, blue, and yellow. But in reality, these are not reds. Red is right here. It's a secondary color. It's a mixture of magenta and yellow. Printer inks actually only produce 3 colors. They only have 3 inks in it. Well, minus black. They also have black as well. So they have 4. They have yellow, cyan, and magenta. So printers have this yellow, cyan, and magenta. And that's the only colors. And they can create any color on the rainbow just by mixing proportions of it. If it's equal yellow and cyan, you'll make green. If it's equal amounts of magenta and cyan, you'll make blue. Equal amounts of magenta and yellow, you make red. And if you mix all 3 together equally, you get black. So mixing of paints and dyes is entirely different than mixing of colored light. If you want to, we're not going to watch this video on this video, but if you want, you can go to this YouTube video and it will show you how to mix all these colors together, and on a kind of a computer they do it, and it's kind of interesting to look at all the combinations. All right, now color by transmission means that light transmits through a piece of glass or something transparent, and if it has some pigments in it, it may allow only a certain type of light through it. So red piece of glass appears red because they absorb all other colors of white light except for the reds. And they can be selected, they're very selective in the material. So if you have gold, and you take gold and you powderize it and mix it in with glass, you will actually make red. And so all the colors, that gold absorbs all the other colors except for red. And same thing, you can have green glass, blue glass, yellow glass, or orange glass. And that's how you can make stained glass windows look so pretty, is because they add different chemicals that will absorb different frequencies of light. So why is the sky blue? Well, when white light travels from our sun and hits us at noonday, the shorter wavelengths, blues, get scattered most, allowing us to see whatever they get scattered in the atmosphere, making the atmosphere look blue. On the other hand, why the sunset is red is because the light has to travel through more of the atmosphere, and the blues, greens, and other colors are starting to get scattered out more, and so what we're left with is a bunch of the oranges and reds. So you can see here, right here is the sunset, and you can see how it's taking out all those other colors, and all that's left is that red. So what color is the water here? Well, it's cyan. And because cyan water molecule absorbs red light, and cyan just happens to be the complementary color of red. So if you wanted to actually check this out, go to a pool, wear a red bathing suit, jump into a pool, go all the way down to the 12-foot pool where there's lots and lots of water between you and them, and you'll notice that your swimsuit that was once red is going to be starting to get darker and darker, looking more and more dark and black. And that's because the water at the 12-foot pool is going to start sucking out all that red light, and all that's left is a darker color, and so your swimsuit will actually change colors. This happens really well with scuba divers. Scuba diving is very anticlimactic if you don't bring a light down source with you. As you go down deep enough, you start losing a lot of color, and so the Discovery Channel, how they get around it is they take big giant light bulbs and shine them down there to give artificial light to see the vibrant colors of the coral reefs. But if you go just with your regular camera and try to take pictures, everything kind of looks a little muddy. It doesn't look as pretty as the original pictures of what you see in the Discovery, and that's the reason why. The complementary color wheel, you've seen this in art. Again, this is the same idea, same principle, that you got your purple complementary color, which means if you mix these two together, you'll get white. And in nature uses complementary colors. The reds and greens complementary colors each other, and they look very, very striking. Your purple and yellows, your blue sky and your oranges, and even nature, even in industry we use it, like our Firefox symbol, which is that blue and orange combo. These combinations look striking, make you pop in nature, and so if you're looking to make yourself noticeable in nature, make yourself look more vibrant to maybe another parrot, and you're like, hey, I'm a parrot, look at me, or a fish, then you're going to look at it. For instance, the bees are going to look at this nice flower. All right, color blindness. This will not be tested. It's just a fun little facts about the eye. So, in the eyes, you have two different types of cells that are light sensitive. You have rods and you have cones. Rods can see in low light conditions, but they only see black and white. They're used for mainly seeing motion. Cones, on the other hand, need high levels of light and are responsible for our color perception. So when you are in the dark room and you turn off all the lights, it's like 3 in the morning, you have to wake up and you're drowsy and trying to go to the bathroom, and you look around, everything will be black and white because there's so little light you will not be able to see much color. And that's because it's just not enough light to actually activate those cone cells. Now, within the cone cells, we have 3 different cells, red, green, and blue, and they come out in these proportions. The proportions aren't really important, but what it is those cells see different colors. And if they will see the Roy G. Biv, or the RGB colors. And so they can see those different colors. So you got your red, your green, your blue, and then here's your cones, or your rods. So now, color blindness occurs when those cone cells don't function correctly. Now, true color blindness, monochromacy, very, very rare, very, very hard. I've never met anybody with it, but they see true black and white. They are completely missing all the cones. They don't see any color whatsoever. That's very rare. Dichromacy is where 2 of them it's missing one of them, or they're the cones don't work. One of the cones does not work correctly, and they can't tell the difference between 2 colors. Red-green color blindness being the most common color blindness. So, if you want to go to this color test, you can just type in color vision testing, and you can see if you are colorblind and having some fun. This website has a really cool where it shows you what the colorblind people see, and you can see that they don't see these pictures. So if you're seeing this picture and you see an elk right here and a bear right here, great, you don't have color blindness. But if you don't see and everything kind of looks like green, yeah, that might be an issue. So if you have any further questions, go ahead and ask your teacher.